I received the parts to redo the eyelet board under the Doghouse. So I've cleared off all the existing components. Here's the pile of parts, and both carbon comp resistors and electrolytic capacitors. Cleaned up the board, it's ready to go. These are all the new parts. I have the 8 microfarad mod caps. I have 20 microfarad. No, these are the 70 microfarads, so I'll use 2 of these in series. I'll go over the schematic. And here are the 20 microfarads. So these things are exact values of the parts that came off there. I kind of wanted to use F&Ts because they just are bigger and they match, I guess, more accurately the sizes of the original parts. And these things are huge, but pretty much all these capacitors are trashed. All the resistors actually measured good. I thought I had a bad 220K resistor, but I think it may have been more of a DMM lead connection problem, and it started measuring correctly when I pulled it out and I moved it around, and it seemed to be stable. But I'm going to go ahead and replace them with these metal oxide 2 watt resistors. Got the values for each to replace each one of those. I'm going to replace the components on the eyelet board under the Doghouse. So these include the 70 microfarad electrolytics in series here at the output of the high voltage rectifier. These 220K 1 watt resistors that bleed the capacitors down. On the other side of the standby switch, we have a 20 microfarad 1K dropper, another 20 microfarad, a 4.7K dropper resistor, 20 microfarad, then through a 27K dropper resistor to this 8 microfarad electrolytic. So these are all the components on the eyelet board. In order to reconstruct this eyelet board, I took a couple pictures of the original showing the electrolytics and the carbon comp resistors. Looking through the pictures, I just have some different shots that show the routing of these cloth covered wires from the underside of the chassis. It shows some of the underside of the eyelet board, showing the grounding, the series connection of the 70 microfarad capacitors, also the connections to the 220K resistors that bleed the 70 microfarad capacitors. Just a couple additional shots showing some detail. So this way I hope to reconstruct it as close as possible. Obviously the new capacitors are not going to be the same size. They're huge in the original circuit, and now they're going to be much smaller with these new mod electrolytics. So this is a nice shot. There's a lot of wires going into this one eyelet. The nice thing about, I guess, the newer parts is the leads are actually smaller diameter. I really like the old parts, and I only replace them if I absolutely have to. But getting 4 wires into a single eyelet is always a challenge, and the new metal oxide resistors and their new capacitors will have smaller leads, and so this will be easier to pull off. I'm going to use the psionic technique of curving these electrolytic capacitor connections as best I can. I watched a lot of his videos, and he's very good at making these boards look nice. Okay, these are the components I'm going to install. The great thing about these kind of components is ESD is not really an issue, so I don't need any anti-static mat or anything like that to handle these. So my goal here is to get these leads prepped. I'm trying to find a reasonable speed for the fast motion stuff. It's nice to see some kind of detail as to what I'm doing. I was using times 15 or something like that before, and I noticed that the videos, you couldn't even see what was going on. This is times 8 speed here, and I feel like it's better than before. I can see what's going on. You can see I'm kind of trying to round these leads the way that I see Psionic, who's a YouTuber, awesome videos on amp repairs. I've learned a lot from him. And Uncle Doug is a good one. He was the first one I found really that was doing the kind of stuff I was interested in, and I watched pretty much every one of his videos, and I pretty much watched every one of Psionic videos as well. The way I use YouTube, I normally will search for some type of amp, specific circuitry that I'm interested in. Started looking at Fenders because there's so much information on the internet about it, and so you can find every detail about every Fender model in the years, and it's probably the best amp for learning the amp repair. And another video I have a Bassman 100, and it has these massive magnetics, and it seems like they're built really pretty well, and I'm impressed by Fender's construction. So the wiring on the older amps is nicely done, hand wired amps, and this 65 here is really no exception. It's some of the nicest looking circuitry I've seen. You just can't get hand wired amps like this anymore unless you go to some boutique. Everything made by Fender is all circuit boards now, sockets mounted in circuit boards, and they do it nicely. They're reliable. It's just not as much fun. The PC boards work just as well as this hand wired stuff. There's really nothing special about this. One thing I did notice is that these newer capacitors on average measure low, and the older capacitors I find in these old amps that are still good, for instance these Astron caps, the ones that were good measured easily to their rated value. There was a lot of failed caps, but the ones that were good typically measured higher than these newer F&Ts and mod electrolytics that I've seen. I'm kind of torn a little bit. I like to have a 70 microfarad cap in the first position, for instance, because the original part value was 70, but I'm not really getting 70 microfarads. I'm getting 60 some, or maybe 60 microfarads, as measured with my LCR meter, but using that same meter, measuring some of the older caps, I'm seeing values that are closer to 70 microfarads. Same with the other caps. For instance, the 8 microfarad cap on the far left, that's actually measuring around 6.8 microfarads, which is sort of disappointing. Definitely is a factor in the sound and its ability to filter ripple and things like that, and also the sag behavior when bus voltage will dip a little bit when you strike your strings, and how far it dips is going to be dependent on these capacitors here. I've heard that these boards are built soldered upside down, and you end up getting like a bulge on the top. I'm not sure if this board is one of those boards. I can see a little bit of an issue right there. It's kind of hard to work with a camera, what I'm finding. Kind of in our way. It looks pretty good. I don't think I soldered anything I shouldn't solder yet, or before I put the wires in. Got wire here, oops, wire here, here, and here. Okay, so I'll need to trim this up first. I'll be better prepared next time to rebuild these dog houses. I learned a couple techniques during this assembly here that will help a lot next time. One last look. It looks pretty well soldered, not too globby. That one's a little globby. I don't think it looks too bad though. Alright. There's not a lot of extra length on these leads going into the doghouse from under the chassis. I cut out part of this video that showed me flipping the chassis over to see if I could get a little more slack in these wires here, but it is wound so tight I just backed out slowly. I could have probably done a better job on this section, but I was sort of distracted by the video aspect. You know, I had this camera in front of me, and I think I got everything prepped pretty well though. You know, there's good hooks on the end of all the wires, and they hook into the eyelet holes, and there's mechanical support there rather than just, you know, lap soldered with lap soldered, which is also real strong in those eyelets. But the idea is to get a good mechanical connection as well as the solder for electrical. Don't rely on the electrical solder connection for mechanical support. There's a clearance concern in the upper right corner. That's a ground wire off the first 70 microfarad cap from the right. There is a high voltage to ground clearance concern right there. That old wire, it's still pretty good shape, the cloth wire, so I just made sure there was some clearance between that ground. Alright, we got a little background noise here from the furnace, but hopefully this records well. There's the completed doghouse bus supply. Looks pretty decent underneath. It looks like everything's hooked up well. I don't see anything that needs to change. As good as we can do it. I don't see any pieces of leads left over from the excess leads from the components. So I'm going to screw it down. I suppose I could apply power and check these bus supplies. All the tubes have been removed. I don't think I'll over voltage anything. I think that could be next. I'm going to go ahead and chop off the end of this IEC connector with the ground, and I'm going to attach the ground to the chassis as well as the power. This is just a temporary line cord. It's not supposed to be anything permanent. It's just for lab test purposes. This will be the first time I've applied power to this 65 Bassman in any way. So I hope nothing else is broken. Okay, plan B, I'm going to go ahead and solder this alligator clip on the ground. I'm going to clip it right on the chassis. Looks like it's got some solder on it. Probably good enough for my purposes. Okay, that's my setup. So I have at least grounded the chassis to the ground pin of the plug. And I should be able to plug this thing in. Are we off? We are off. We're on standby. And all the tubes are out. Just for sanity check, I'll look at the voltage. I'm sorry, I'll look at for any dead shorts or anything weird like that. Wide open up. I turn on the switch. That's pretty high impedance. I'm sorry, that's pretty low impedance, but that's because that's the transformer primary. So I would expect that to be the case. Open, off, and standby switch is off. So the secondary should not be applied to anything but the 2 series electrolytics. With the power switch on, we should see the impedance of the primary of the transformer first. I'm measuring the impedance across these 2 pins. So this looks reasonable. I could at least apply power, but I'm going to plug this into the variac anyway with the current limit. Okay, we have the variac plugged into the current limit, so I may reverse that. Should I reverse that? So this is plugged into the wall, and then the output of the current limiter goes to the variac, probably fine. For my purpose, I'm going to turn the variac all the way down. We're actually on at this point. Actually, this is maybe a better spot on the ground switch. Let's find out if this is a 3-way ground switch. No, just 2-way. So you either get neutral or hot of the line connected through a cap to ground. Let me go ahead and bring up the voltage a little bit. Let's watch it. No voltage coming in. Let's see, why is that? Just try the other side of this. There's my voltage. Okay. There's our input voltage so we can see. Let's just put 15, 17, 18 volts, whatever. Let's see what we get when we enable no drop in voltage. So that's looking pretty good. Let's look. We can look at the output of the transformer. In this case, it should be on. Yeah, there's the input. We have bus. Okay, right here is where we want to go. Let's go right across the input to the bridge rectifier. And we have no voltage. Interesting. I think we have power on the, we might have a blown fuse or something. Not a fuse. The fuse may be blown, actually. So let me shut off the juice here. I need another meter. Just a quick test of this fuse. Nice alligator clip on this guy. That's perfect. Okay. And yeah, blown fuse. So something went wrong, and not surprising. I mean, the caps in the power section, we're all toast. And I'm not sure where the short is, but I hope it's not that power transformer. I guess we'll find out here pretty quick. We have power limit. So the fuse is a 2 amp slow blow. So I might go for a 2 amp fast blow for now. All right, I have a fast blow fuse. I'm just going to go ahead and use that. Our power is off. We should have low impedance here. Yes, we do. That's the secondary, which is a nice higher value. It looks like the secondary is intact of the high voltage. So we're going to go for the output of the transformer here on the measurement of AC, and I'm going to go ahead and enable this. And we see voltage 66 volts. Excellent. So the transformer seems to be functioning. We have some lower voltage on the input, probably 10 volts. Looks like, yeah, 10 volts. All right, more like 10%. So we should be able to bring this up. And okay, there's 100 volts on the output of the bridge. I want to now turn this back off. We'll flip it over. I think we're pretty good at this point. I'm going to go ahead and flip this over. We're off. No power. Okay, so now we're going to look at the output of the transformer at the series cap. So we should see the full DC voltage. Yeah, it still has 15 volts from being charged previously. So we should see, I would think over 100 volts when I enable the output. Well, we'll turn on the power first. There should be okay, actually, this doesn't seem that high, 67. Oh, because I turned this down. So we do have the DC voltage. This is the output of the rectifier. So everything's looking pretty good. I'll just do, at this point, I'm just going to do a low voltage test anyway, just to make sure my wiring looks correct. Okay, there's this point where the red connector is on the standby switch. So the output of the transformer and input of the standby switch. So the other side of the standby switch goes through a choke and to the output transformer center tap as well. So this should be the output of the standby switch. Yeah, see, we left the standby switch on, which makes more sense. I mean, when you've got the amp on, you want both these switches in the same orientation. So the main power is on. The standby switch is now off. You can see this 220 at least discharging. I would expect we'll see down the line voltages on every one of these. And we do. So that's a pretty good test already, that we at least have the caps installed and they're connected to power. Maybe I'll leave it that. So as I enable the standby, take it off standby, you can see that's the very last 8 microfarad capacitor in that anode supply string, and I can see 61 volts. As I move back up the string, I should see, there's really no voltage drop across this because there's no load. There's very low current I expect going through these first, the 1K, for instance, to see how much current we're. So there's literally no voltage here, so we are not drawing any current through the bus supply, which is a good sign, because there's no load on it. All these tubes have been removed. I could go ahead and watch this current bring up the voltage, and you can see there's some current now as I brought the voltage up 20 on the variac up to 20%. So we do now have some dropping going on. Let's see how this looks. Okay, on the input, 100 volts. Okay, now we're at 100 volts to the first, 100 volts to the first. Now we should see a little drop. And it's still not red. It still doesn't register. And it's starting to drop a little bit. 96. So let's bring this up just a little more. Let's go to 150 volts on the very last. So we have 150 volts. What does it take to get 150 volts? 160 volts. And then through the resistor drop, we see it drop down to 156. Let's take another quick look. Between these two legs, I don't see a lot. 0.6 volts, still about the same as it was before. There, let's go this way. 0.6 volts. So that's 1K dropping. So that's like 500 microamps or something like that, right? Because we got 0.5 volts divided by 1K should be 500 microamps. Here's another drop. This one has a little larger. There's 1 volt across a 4.7K. There's 200 microamps through that. We're not talking about huge currents here. Then the very last leg, this is actually a 27K, 10 microamps to the last capacitor. So let's write down these values for fun. Here's ground. We have 162 volts DC. And this is a cross choke. And this is 0.034 volts. 4 volts. Now let's go back to ground here. What do we have? At the 1K, we see 161.7 and 161.4 at the 4.7K. And then finally at that is a 27K, we see 161. So a little bit of voltage drop down the string with no load. Might as well watch the discharge on this. Okay, so I'm at the very last value. When I go on standby, we can watch basically all these secondary capacitors discharging at that rate. Let's do this. Let's hook up. See how these series caps are sharing their voltage. So there's the ground, and we're on DC, and this is the middle point. So we turn the output on. Sorry, we're on standby. We have to go ahead. Okay, I'm an idiot apparently. Why are we not seeing anything here? We should see some voltage. It's like I didn't turn something on. Hold on there. Okay, I guess I'm a moron. I don't know what's going on. I see. Okay, we're going back on. Okay, we got 163 volts, 164 volts across the whole thing. Halfway point should be, I don't see anything. Why is that? Oh, because, no, that's exactly where it should be. I don't see any voltage. How come? Because I think I have problems with these. I must have a broken wire in my, because there's definitely voltage there. I bet if I touched it, I think there probably is voltage. I think there's something wrong with my test leads. Let me swap them out. Colors are all messed up. But, okay, we have nothing here. I bet you if I hook this up, it's going to be common. I'm going to use this one for common. And then this one for hot. And I'll get some better cables, but I bet you I have voltage here. Yeah, and so I think I have at least one faulty test lead there. Hopefully we'll see half the voltage here. And we do. It's very close to half the voltage. So 220 k ohm resistors are helping these two caps share. They're fairly well matched, and it sort of helps them share the voltage, as well as being bleeders, as well as probably affecting other characteristics of the sag of the bus during operation. Okay, I am going to go ahead and look at the voltages across each of these. Still in DC. Okay, more data. We now have to take it off standby, and across 1K, we're going to say 0.27-ish. Oh, it's sure bouncing around. I want to look at that on a scope. 2.24. It's draining down. Why is that? It's going down. So something's charging up downstream, I would say. Slowly charging up. And then we do have, somewhat high resistors down the string that probably take a while to equalize. Okay, so I'm going to say 0.2 volts across 1K. I'm going to say 0.2 volts. Okay, and now let's move down the line. Now this one across this is a larger value. I think it's a 4.7K. 4.7K. We see 0.45 volts, we'll call it. Okay. Moving down to the next one. To the 8 microfarad spot, we see this is across 27K is 0.18 volts. Okay, that's probably enough information. It's nice we see this series arrangement sharing properly, so that's more evidence that the update to the circuitry went okay.